Anyone say more? Alright, welcome everyone to this very first preview session of POPL'24. So the concept of preview session is to make the technical tracks both more accessible and to give a bit of background on them by asking people who are experts in the field to introduce us at these sessions. So we're going to have our first two preview talks, starting with Xiaokang and then
Alright, so good morning. Welcome to the session preview for 2021. So that means we have actually two preview sessions this year. And in recent years, every POPL year has at least one or two preview sessions. So it's really an active and exciting portfolio. So let me start with an overview of some history and some challenges. So simply put, program synthesis is to object generate programs from scratch. This is one of the oldest problems in computer science, studied by the pioneers like the first in the early days of computer science. And this also is one of the most challenging problems. Everyone knows it's so challenging, and it's more like a dream. Involving the standards of program synthesis, we will talk about two in the title. And the one illustrated of mine is from So everyone knows this is challenging. But things probably with 2000, we have seen a revival of these areas, and it has to be possible so that users can be tracked to actually do some domain. And then one of the most prominent examples is from Microsoft, especially people in Microsoft Excel. The user writes in some of the examples so that program can be installed in this makes program synthesis techniques accessible to users. And since then, the area has attracted a lot of research, and machine learning has been very successful now alternative as well. And we are all talking about large language models today. So the dream has come more closer to these tools, but there's still a long way to go. Alright, so remember the synthesizer takes the user intent and produces a program. So the challenges come from every step. Okay, what should be the user intent, how the synthesizer should work, and what programs do you want to do. So the two steps are intention, and and following the categorization from the different programs, categorization and intention. Or skeleton of the program. And invention is just what's happening under the hood. Right? How can we search the space? And adaptation means that we can have many programs satisfying the specification, right? But not all of them are born equal. Some are better, sometimes we want an optimal one, sometimes we want to satisfy some quantitative metrics. The super optimization from the compilers community can be viewed as a kind of adaptation. Alright, so in this session, we actually have quite diversified talks covering all these three categories. So let me go through them one after another. So the first talk is from a set of researchers from the University of Utah, and it's actually a paper and the Distinguished Paper Awards that will give you one more reason to attend. So the motivation is about how can we implement mass library functions more efficiently. If you do it in C, for example, right? It's quite tedious. It does not give you much hint about how to detect the mathematical errors, how to tune the precision and performance, etc. So this is like a great application domain for program synthesis. So it covers both intention and adaptation. right? We want to make it a more user-friendly way, and also we don't want to give up. We want to keep up with the precision, performance, all the nice things we expect from math library. So the solution is a domain-specific language called MegaLibM. All right. So the idea is to split the high-level concern and the low-level details. Okay. At the high level, you start from picking some right polynomials. So any mathematical function should be represented by a polynomial. So you pick a polynomial and you start doing some simplification, range reduction, or identities, so that you get the polynomial simplified. Then you are ready to tune all the details. What's going to be the floating point number? What's going to be the precision? And there's a compiler to see, so that you can easily get feedback to tune about the performance. So this is an interactive way of implementing math library functions. So as a result, they can replicate a lot of existing math library functions in C and also create some new library functions. So that's really promising. Our second paper is from my own group. They invited me to give a talk, so I don't think I have conflict of interest. So it's more about invention. Okay. So, and the context is about bit vector synthesis. We want to synthesize bit vector expressions. And in this area, we are not up with human intelligence. Right? For example, in the Hacker Delight book, there's a lot of tricky and elegant expressions handcrafted by human. Right? And we are not there to synthesize all of them. So how can we get them automatically done? So there's a lot of progress. People know how to do bottom-up enumeration, top-down deduction, right? But we are still not there. And the key idea, one of the key ideas in the paper, is to have a novel combination of these two ideas, which we call bottom-up deduction. Okay, we do enumeration and we also do deduction on the fly, so that we can get more scalable synthesis algorithm. And we have 6 new Hacker Delight examples synthesized for the first time. The third paper is also about invention, but in a different context. So here is a technical problem called observational equivalence. Right? So to check a program, or to synthesize a program, you want to keep track of the variables, right, and see how the variables are updated, so that you can check the equivalence between programs, so you can have a symbolic nice representation. The local variables in groups makes a trouble, right? Because it's a local variable. You have, before you have a program, you don't really know which values of the local variables are relevant. You need to have a program first. If you have a program, you don't need to do synthesis. Right? So this is a technical problem, and they solve the problem using an idea called lifted interpretation. All right, so they extend the representation of finite tree automata, so that it can be extended on the fly. Whenever you see a new value that is relevant, you can extend the finite tree automata to handle that context. So a very nice idea. And as a result, we have a lot of web automation tasks done faster than before. Last but not least, we have a paper from a set of researchers from UPenn. So this paper's focus is on adaptation. Remember, we want to have optimal program, right? Optimal program synthesis. And here, let's say you have a parameterized program. For example, you have an image and you want to determine it's a cat or not. The program can be parameterized, and you want to tune the parameter so that you maximize the accuracy. So how do you get this job done? The researchers proposed an algorithm. This is basically an A-star search algorithm. And they determine the heuristics. They determine which direction is more promising based on abstract interpretation. For example, if you have an abstract category, okay, the parameter is between 50 and 100. All right. So what's the best possible accuracy I can get? Right. So that can be computed through abstract interpretation, and that can guide the search, right, steer to the optimal program more efficiently. So what's the result? First of all, you have guaranteed optimality, right? So this is important. This makes synthesis different from machine learning or black box based methods. And also it's faster than all state of the art. For example, MetaSketches was an optimal synthesis algorithm, and we get better performance here. Alright, so that's all I have to say, and see you in Kelvin lecture at 10:30. Thank you.